Hi everybody, welcome to another video in Calculus 3, section 17.4, Green's theorem. This is one of my favorite sections of the whole calculus book. So what we've been studying is the line integral. We write in this form, vector field f dot product with dr along a curve C. Now if we write vector field f, let's just say two components, f and g, if we have one more, h. And if that is the case, vector r is the vector of just x and y. So in that case, dr is equal to pretty much dx and dy. Or if we multiply and divide by dt, we can write dr is equal to dx over dt, dy over dt times dt. And then of course that is the derivative. From t dt. Of course we use this quite often. So we can use dr any of this. But if we use f of this form, then we can write the line integral. Equal to that vector field. I just write two components just for the simplicity of it. And then dr, you can use any of this. I'm going to use this one. The dot product gives us f dx plus g dy. Usually in the Green theorem, you will see the line integral is given in this form, but actually that is the same thing as this one. Right. Now since we reviewing in section 17.2, we write this. We define the line integral a little bit differently. We're not writing in this form, although I prefer the line integral to be written in this form. But first we talk about integral. We define not in this form, but we still have the vector field f, but that dot with the unit tangent vector times ds. So in this particular case, f is still a vector, which is f and g, so there's nothing new here. But the unit tangent vector is a little bit different. It is unit tangent vector, meaning that t is equal to a tangent vector, which is the derivative, and it is a unit vector, so we have to divide by the magnitude. Right, so that is t. And what is ds? Ds is the length, so we have to consider this. So we talk about this. Ds is the length. Even by Pythagorean theorem, we can write as ds is equal to square root of dx squared plus dy squared, and divide by dt square multiplied by dt square, we have dx square over dt square, dy square over dt square. So we divide by dt square and multiply by dt square. Right. Now take the dt square on the outside, so we will have the x over dt, that is derivative of x with respect to t square, and derivative of y with respect to t square. That's what we have. The dt inside the square root, bring it outside, become just dt. Now, this is actually the length of the tangent vector. So we have ds is equal to t dt. Now we substitute everything into this integral. I just want to review a little bit different forms of the line integral, because you might see the Green theorem in the physics book or engineering book, and they can write this in many different forms. Right, now I'm go back to this t ds. Right, now f is still a vector field f, dot product, unit tangent vector. I'm going to use that. That the tangent vector divided by the magnitude give us the unit tangent vector, and the ds, I'm going to use this. And cancel that out, we have just f dot r prime t dt. Of course, which we use a lot. Yeah. Of course, we should write the vector field f as a function of t. Yeah. Of course, we use this the most often. Here we just write the limit for t, let's say from a to b. So you can see the line integral in many different forms. It could be in this form, which I prefer. The Green theorem usually written in this form for a reason, and then all the definition in the textbook, the definition in our textbook, we use in this form, which is of course the same thing as that. So all of the form are equivalent. Right, just different form of line integral, but we focus on this one. Right. So that is all the different forms of line integral. Now, in section 17.3, the previous section, what we study about is we focus on the type of a vector field is a conservative vector field. If the vector field is conservative, there will be four things, right? Vector field conservative, there's a potential function independent of path, and line integral on the closed curve is equal to 0. So those four things are equivalent. I assume that there's some details I have to satisfy, but like I said, we're not focus on those tiny details. Right. In this section, the Green theorem, we focus on a special kind of line integral. First of all, the function here most likely is not conservative. I'll explain why in later part of the section. So the vector field here may not be conservative, but most importantly, in the Green theorem, we only talk about two dimensions. So that's why when we write like this, we specify that it only have two component functions. So everything in R2. So Green theorem in R2. The vector field Green theorem, the vector field is in R2. So two-dimensional vector field, and C is a closed curve. So those are special case for Green theorem. And because it is a closed curve, we're going to use this notation. the integral with the circle. So C is the closed curve. So we just write like that. Right, so either we write that form or we write this form to underline the fact that this is a two-dimensional vector field, and the Green theorem say that equal to this. By the way, did you see this one from here? If we have the equal sign instead, that is the condition for the vector field to be conservative. Now, if the vector field is conservative, this is equal to 0, so this is equal to 0. So that's why I mentioned earlier, if the vector field is conservative, the integral equal to 0 here, because for the closed curve, vector field conservative, the line integral would be equal to 0. So we more than likely, when we use Green theorem, the function, the vector field is not conservative. Otherwise, we just have 0. There's nothing really matter. And here we define a two-dimensional curve, which is what we mentioned before, derivative of g with respect to x minus derivative of f with respect to y. And that's pretty much what we have here. Yeah, that's what we have. We call the curve two-dimensional curve. Right. So of course we have to have the curve have to be closed. Most importantly, of course, they have to be smooth and oriented counterclockwise, and enclose the region that is connected or simply connected region in the plane. Right. So the Green theorem says that the line integral on a closed curve is equal to the integral, a double integral of the interior. So in this case, the most, along with the fact that the vector field is two-dimensional and the curve is closed, there's also one more thing that is important, is that C is the boundary of R. So the curve C is boundary of the region R. Right. Now let's look at the first example here. Let the vector field be 0, 3y, and the region R, that the unit disk, and C is the boundary of R. So if it is the unit disk, the boundary is the unit circle, and we have to specify that it is counterclockwise. Now verify the Green theorem by evaluate both line integral in the theorem. So we're going to do both of this. Right. So first we will do the left hand side. We just do the line integral. So we use the left hand side. We're going to do this. Or we can write as f dx plus g dy. And we're going to do this first. So first we have to parameterize C. So this is the standard line integral. So first we have to parameterize C in terms of one variable. So parameterize C. This is x squared plus y squared equal to 1. So typically we will let x equal to r cosine theta. We can use t or theta. And the radius is equal to 1. So in that case we just have cosine and sine. Right? Because cosine squared plus sine squared is 1, and t is between 0 and 1. I mean 0 and 2 pi for the whole circle. Right. So we'll have the parameterize the curve of t equal to cosine of t and sine t. Right. in that limit. Right. Next step is we write the vector field in terms of R. So 0, y is sine t, so we have 0 and 3 sine t. Right. The next step is we write dr. Or we can just write this. In fact, let's just, because we can find dr, but if we focus on this form, never mind, I just want to find dr here. It's r prime t dt. The derivative of cosine is negative sine t. Derivative and then cosine t. That's the derivative, and then times dt. Right, finally, we put in the line integral. Equal to we write the vector field in terms of t, and then dot product. T go from 0 to 2 pi. So we have the integral from 0 to 2 pi. And the vector field 0 and 3 cosine 3 sine t dot negative sine t cosine t dt. So 0 to 2 pi, and the dot product give us 0 and 3 sine times 0 times negative sine t, that's 0 and 3 times, so we have 3 sine t cosine t dt. Right. That equal to 0. Okay. We use the double angle. Yeah, we should choose a vector field that is not conservative. Anyway, so 3 sine t cosine t, we use the double angle. Sine t cosine t equals sine of 2t divided by 2. That gives us 3/2 sine of 2t dt. And the integral is negative 3/2 cosine of 2t divided by 2, all from 0 to 2 pi. I put 0 and 2 pi here, we have the same value, so that's why this is equal to 0. Right. Actually, we should have a much better example than this. That's fine, we have plenty of example. So that is one way to do it. Another way to do this is we write using this form, though, right? So we're going to, if we want to write this form, so we write vector field f is equal to f and g, which is 0 and 3y. So we can say f is equal to 0 and g is equal to 3y. Now, the parameterization we did have of t equal to cosine and sine. So when we write like that, we mean x is equal to cosine t and y equal to sine t. So with this we have dx is negative sine t and dy is cosine t. And we put them together in the form f dx plus g dy. Now if we put everything in terms of t, we will have f times dx, negative sine t dt, sorry, forgot the dt, negative sine t dt plus y plus g, in this case 3y, and y is sine t, and then we have times cosine t dt. So that is equal to 0, and so we have 3 sine t cosine t dt. T go from 0 to 2 pi. So whether we write in this form or we find f and then g and then dx and dy put in this form, they should be the same thing. Either way, that integral equal to 0, right? So we can write like this too if we want to, or we just write like this. So that is the left hand side of this. Now we use double integral. Of the interior. Right, so this is a double integral over the interior of the region. So first of all, we can write this as double integral. This is a disk, but we talk about the interior here. Disk of radius 1. And then just going to write derivative of g with respect to x minus derivative of f with respect to y dA. Now, from the vector field here, we have f is 0 times from here we can say the vector field f is equal to fg 0 and 3y. So f is equal to 0 and g is equal to 3y. Then we can find partial derivative of g with respect to x. Derivative of this with respect to x is 0. And derivative of f with respect to y is 0. So finally we write this integral. Derivative of g with respect to x minus derivative of f with respect to y, both of them are 0, so we just have 0. So that's why this is equal to 0. Right. So both of them are equal. So once again, there's a lot of different ways to write this. The standard line integral, that's what we do. Or we can write the integral using the form of f dx plus g dy, which is the same thing. Or we can use the area, the double integral of the interior. Right. So bottom line is, put this together, we will have, I will write this theorem for this particular problem as follows. So instead of doing the line integral, on the boundary. So I'm just going to say it. Boundary counterclockwise, unit circle counterclockwise. This is the same as doing the double integral for the interior, and the price to pay is, instead of f, this have to be derivative of g with respect to x minus derivative of f with respect to y. Yeah. So line integral on boundary oriented counterclockwise is the same as double integral on the interior. Right. And some books they even write if this is the region D, so they write this on the region D. And then here they write the integral, line integral on the boundary of D. And then to say that's like the simple partial derivative. Yes, it is. And that is sometimes referred to the boundary of D. So yeah, so I see it in this form also. By the way, there's a reason we use that symbol for a boundary. Think about this. What is the area of a circle, area of a disk? Pi r square, right? If you take derivative, that gives us 2 pi r, which is the parameters, which is the boundary of a disk. Likewise, 4 pi r cubed, 4/3 pi r cubed, that is the volume of the sphere. If we take derivative of that, we have 4 pi r square, which is the surface area of a sphere. This is the area of the ball. So pretty much we take derivative, we get the boundary. Take derivative of area, we have the parameter. So there's a reason that sometimes they use that symbol. Of course, they have a lot more advanced theorem that led to using that notation. But like I said, the green theorem, we can use double integral to evaluate on the boundary, or we use the boundary, use the line integral to estimate, to evaluate the double integral inside. Whichever one is easier to do. In this case, I'm doing both sides. Right. So that's the first one. Next. Now consider the vector field F, two components. So evaluate that. C is the closed curve, and C is the unit square, 0, 0, going from 0, go to counterclockwise. Right. So on the big scheme of things, this is what we have. Vector of two components, which is good. If it's 3 components, there's something else. There were 3-dimensional version of the green theorem, which we call the Stokes theorem. That is section 17.7. Right now, we only focus on the green theorem. So green theorem. In this particular case, we have the line integral over the unit square. Unit square going from 0, 0 and go counterclockwise, so go counterclockwise. Yeah, so the line integral go over the unit square. The green theorem say, instead of doing the line integral on the parameters on the outside, we will do the double integral on the interior. And the price to pay for that is dg minus df dy dA. So in this particular case, we have a unit square. So instead of doing the line integral along the boundary, we can say it's double integral over the interior. Right. So this is the vector field F. And if we have to do line integral for a square, that will be 4 line segments, 4 different parameters. So that sounds like a lot of work if we do the line integral, because that we have to do all 4 of them. that's a lot of work. So let's do this, especially the function here doesn't look like something nice and easy to do. So we have the vector field of two components f and g equal to 3y plus sine square x minus tangent y square. Right, now let's evaluate the derivative of g with respect to x. So in Green theorem we need to evaluate that derivative of f with respect to y, right? Derivative of g with respect to x, this is just 1, and the derivative of f with respect to y is 3, so that's 4. So that's why the sine square and the tangent y square here doesn't affect anything on the line integral. So doesn't do, I mean, just say doesn't do anything contributed to that integral. So that's just whether we have those terms or not, it doesn't matter. Green doesn't care about that. Right, now we write this again. Now if we want to do the line integral on the boundary, or we can just write in this form if we want to, it doesn't matter. F dx plus y plus g dy. Either way, Green theorem say this is going to be the double integral on the unit square, and just going to write derivative of g with respect to x minus derivative of f with respect to y dA. So we have and that is just equal to 4, right? So this is 4 times, I take the 4 outside. What we have here is just the area of that unit square, right? The area of that unit square 1 by 1 is 1. So the answer is equal to 4 times 1 equal to 4. Because 1 is the area of the unit square, right? So you see the Green theorem is extremely helpful here. We use Green theorem, we don't even care about those two functions. And we just calculate the area. We don't even integrate here. We just use geometry. The area of that unit square is 1, so 4 times 1 is 4. So that turned out to be very, very nice. All we need to do is just evaluate this. So when the curve is closed, we're going to use that for 2 dimension. For 3 dimension, that will be a different case. Right, now just notice that the Green theorem, or like any other equation theorem, when we have 2 sides, we can use one side to calculate the other, or we use this side to calculate this. So one side is line integral, the other side is area. So another application of Green theorem is we can use the left hand side here to calculate the area. So if R is the plane region bounded by a smooth curve C, oriented counterclockwise, like I said, those are important. Close counterclockwise. Then the area of R is given by. So pretty much we just do that integral. In order to do this, we have to parameterize. Just like any line integral, we need to parameterize. By the way, we can use that, or we can use the formula of just x dy, or if we just want to use negative y dx. Yeah, either one of those, but in the standard way we use this one. Right, an application to this is planimeter. So let me show you this real quick. So all you do is just type Parameter and give us the device like this. So what this device does is will trace the parameters and give us the area used to determine the area of an arbitrary two-dimensional shape. So let's look at an example here. Right. So we have a map. So in this case, if we can give the boundary, it will calculate the area for us. So let's look at Texas here. All I do is I just click at the point. One, two, three. I just click on the boundary. And if I can specify a boundary, things here. Right, that's about right. So when we click on the boundary, we scroll down and give us the area. So the area, by the way, not only that, they give us the parameter of that too. So in this case, if that is the boundary, we have the area is 2.66 times 5 square miles. So what's that about? 266,400. So estimate is about estimation is about this much. Right. Now let's go back. And let's type area of Texas. So we have 268.5 square mile, which is very close to what we have. So we have that much, which is very close to what we have here. Very close to what we have here. 266.4. So this is what we have compared to the actual area. So that's very close. So if we can specify a boundary, we can using this method, we can estimate the area inside. So if we give the boundary, it will give us the area. So if we zoom in, we can find the area of a lake or area of a house or something. So this is very powerful tool. Right. Since we here, I just want to show something that I forgot to mention in the section where we calculate the center of mass. So if we talk about center of mass of, let's say, a US, assume that it is a thin plate, then the center of mass of 48 states is at this point, Lebanon, Kansas. So there's a picture of that. So this is the area. It is the point. It gives the coordinate and all, and this is at Lebanon, Kansas. It is the center of mass of the U.S. This is in 1940, which is before Hawaii and Alaska joined the Union. So if we consider Alaska and Hawaii, the center will shift to the left and north. So in that case, we will have this center of mass will locate at, where's that? Yeah, in South Dakota. Yeah, it's Belfort, South Dakota. Here, right? So we have the center of mass of 50 states. This is after 1959. At this point, and this is the center of mass of 48 states. What I don't know is why they have the same bird here. It looks like the same, maybe the same person taking the picture, but that is another question. Anyway, we'll go back to the section. So bottom line is, if we can specify the boundary, then we can calculate the area using that. And that's exactly the planimeter device do. They can do some different calculation, but the idea is, if we can specify a boundary, it will calculate the area inside. That's what this device does. Right, now we'll use that. We use one of those to find the area of an ellipse. So we will have, in order to find the area of the ellipse, I will write the green theorem as follows. So if we want the area of an ellipse, it is equal to 1/2 of dA equal to 1/2 the line integral of x dy minus y dx. And if I do that, it will be on the boundary oriented counterclockwise. So that's essentially what the green theorem is about. We can do the interior double integral for the interior, or the line integral on the boundary. In this case, we will use this side, the right hand side, to evaluate the area. So we're going to do this. If we're going to do the line integral, always the first step is parameterize the curve. So parameterize the curve C. It is in this form. So naturally we let one of them be cosine, the other one is sine. Usually x we go with cosine. So x squared over a squared equal to cosine squared, and then y squared over b squared equal to sine squared. In that case, add sine by sine, cosine squared plus sine squared equal to 1. So that makes sense. Like I said, usually we let cosine associated to x. In that case, it will go counterclockwise, easier. Right. So multiply the a squared. So I have x squared equal to a squared cosine squared t, and take the square root, we have x equal to a cosine t. Then we have y squared equal to b squared sine squared t. So y equal to b sine t. Right. So usually when we do the line integral, we need to identify the parameters. So here we can say the parameter is a cosine for x and b sine t for y, and one complete revolution, meaning go from 0 to 2 pi. Right, so we have the parameterization of the curve. Next, usually we will write the vector field f in terms of t, and then dr in terms of t. And what we do here, we write f in terms of t and then dr in terms of t. This one we don't have to. We're just going to calculate. We're going to write x, we have x. Y, we have y. We just need to find the x and dy. So x equal to a cosine t. So derivative of x with respect to t is derivative of cosine is negative sine. So negative a sine t dt. So that is dx. Y equal to b sine t. That derivative dy is equal to b cosine t dt. Alright, and finally the green theorem. Area equal to and that equal to the line integral, that's 1/2, sorry, on the boundary, or counterclockwise. of x dy minus y dx. So now if we write everything in terms of t, that will be a lot easier. So 1/2. Now we write in terms of t, x is a cosine t, dy is b cosine t, minus y b sine t, and dx negative a sine t dt. Right, that gives us 1/2 ab, limit for t 0 to 2 pi. Yeah. So if we write in this form, we just find x and y, and then the x and dy, we just substitute in that. So we have ab cosine square and minus negative, that's a plus, ab sine square. Now cosine square plus sine square is 1, right? So this turn into this integral. We just have ab dt. All of them are constant. So the integral equal to 1/2. ab is constant. I will take outside of the integral, and then integral from 0 to 2 pi of dt should give us 1/2 ab times 2 pi. So we have pi ab. So pi ab is the area of an ellipse, which is turned out to be very nice. By nice, I mean if we have an ellipse like this, this is A and that is B. So the area is pi AB. Of course, if we have a circle, then this is the radius R, that is the radius R. So the area is pi R times R. So that's consistent too, right? So as you see, in this case, calculate the area of an ellipse is a lot easier to do than to do the double integral, because this is not quite polar coordinates, so kind of difficult to evaluate it. But parameterize the curves, not that bad. The line integral is easy to calculate. That gives us pi AB, which is very nice. So, as mentioned, the Green theorem, there are two sides of the equation. We might use the line integral to evaluate the area, or we use the area to evaluate the line integral. So whatever is more convenient. Right, okay, let's look at a couple more examples. Consider the vector field y square and x square on the half annulus, and so the curve is inner radius is 1, outer radius is 3. So very much we talk about this. We are talking about this region, and also the orientation is below, so we go in that direction. So the significance of this is that direction. With respect to a point inside here, we go counterclockwise. So Green theorem is have to go counterclockwise. So that's why sometimes you will see the integral. Normally we write the line integral like this. Sometimes we specify the direction of it to go counterclockwise. But I don't know how to type that notation in the note, so I just write a circle. Anyway, so we calculate the line integral on that. Now the Green theorem, let's just write the Green theorem. Now what we want to calculate is line integral on the boundary. Rather than write C, by now probably you know that I prefer to just draw counterclockwise. counterclockwise. Yeah. So we do line integral on that. Green theorem says instead of doing that, we can just use the area of the interior. Yeah, I could draw better than this. So instead of do on the boundary, we do that on the interior. And so instead of the function f, we have to write g with respect to x minus f with respect to y. If we happen to forget that, it doesn't matter. Remember, that is a two-dimensional curve. Yeah. So we write like this: derivative of g with respect to x minus derivative of f with respect to y. So, alright, 2 by 2 determinant. Right. Now let's do d of g, dx, and f and y. So let's write that out. So this is the function. This is the vector field, sorry. That means f is y squared. First component. The second component is x squared. G equal to x squared. Now we do that. Derivative of g with respect to x, that would be 2x. And derivative of f with respect to y, 2y. So then we're going to substitute that in there. So this integral is equal to, once again, I'm still drawing half a donut. And the function is 2x minus 2y dA. Right. Now if I write the limit for the donut like this, it will be in rectangular will be a lot more difficult. I can just say for that donut, r is between 0, not 0, from 1 to 3, right? Because x squared plus y squared is r squared in polar. So this one in polar coordinate. R is between 1 and 3, and theta 0 to pi. So in polar, we're just going to write like that. So that integral to x minus 2y dA over half a donut we can write x in terms of polar and y in terms of polar. In polar, x equal to r cosine theta and y equal to r sine theta. So in this case we have x is 2 r cosine theta minus 2 r sine theta. Don't forget the a r dr d theta. So the limit for theta go from 0 to pi, and the limit for r go from 1 to 3. The limit of constant function is separable, so I will write factor out the 2r. We have cosine minus sine. Oh, and then the r here too. I will multiply the r with the 2r, make it 2r squared, right? So factor out 2r and multiply with this r, give us 2r squared, and then dr d theta. Right. For linear theorem. So we write that as a function in terms of theta, and then 1 to 3 to r squared dr. Yeah. So what is the integral of cosine? Sorry, math number 9. We go from 0 to pi. Cosine minus sine. That is -2. Yeah, this is in gradient. Okay. And then the other integral from 1 to 3 for 2r squared. And we have 52 over 3. So that is -104 over 3. Right. So this is a lot easier to do on the line integral, because if we do the line integral, there will be 1, 2 line segments and 2 semicircles, so there are 4 segments. It's a lot easier to evaluate. So use the area for the interior. It's a lot easier to do. Right. Next, we will do this one and consider vector field on the curve on the boundary of the region bounded by those two functions. And going counterclockwise, of course, those are all the ingredients for the green theorem. Find the line integral. So in this case, once again, we find the line integral. So we can use the green theorem for the interior. It will be easier to evaluate. So I just draw just a sketch. I will just sketch the region. Y equal to 4 minus x squared. And y equal to 0. So when we make these two equal each other, x squared equal to 4, so x equal to -2 or 2. So we're talking about the interior here. So the green theorem, rather than do the line integral on the boundary, or counterclockwise, we can just do the double integral on the interior. The price to pay is derivative of g with respect to x minus derivative of f with respect to y for that vector field dA. Right, so that is the action of the green theorem. Now, the vector field is here. F, the vector field is 3y plus e to the x, and then x squared. So for this, we have f is equal to 3y plus e to the x, and g is equal to x squared. So we're going to calculate that part. Derivative of g with respect to x minus derivative of f with respect to y. G with respect to x, 2x. Derivative of f with respect to y. So that's just 2x. Derivative of f with respect to y, just 3. So that's what we have, right? Simple enough. So get back to the integral. Now what we have inside is 2x minus 3. Just write this for once. Now that's just 2x minus 3. dA could be dx dy or dy dx. For this double integral, I will just, if I look in the y direction, we see y equal to 0 first, and then the parabola y equal to 4 minus x squared. So if we go along the y-axis, y equal to 0 to y equal to 4 minus x squared. If we put the y first, and then the x on the outside, just go from -2 to 2. So that is the double integral. -2 to 2. And we integrate this to x minus 3 with respect to y. That is to x minus 3 times y, right? Because 2x minus 3 is constant. Evaluate from 0 to 4 minus x squared dx. So the double integral, I evaluate the inner integral. I cannot use Fubini theorem in this problem because the limit here is not constant. If the limit are constant and the function are separable, I always use Fubini theorem. Right. -2 and 2. And if we put 4 minus x squared here, we have something. If we put 0 in here, we have nothing. So 4 minus x squared. And then to put in 0, we have nothing. So that's why we just have dx here. Right. I just do this quickly. -2 to 2. To x minus 3. And 4 minus x squared. It's -32. Right, let me just multiply this out real quick. Ax minus 2x cubed minus 12 plus 3x squared. Right. This one, if we have to do by hand, this will be equal to 0 to 2, 2 times -12 plus 3x squared. Right, why is that? Right. Focus on those two functions first. Ax minus 2x cubed. It is an odd function. If it's an odd function, the limit of symmetry, we have something above, something below, which are the same area, so they cancel out. So if it is an odd function on the boundary, on the limit that is one positive, one negative of the same number, then that one integral will be equal to 0. If it is an odd function, if it is an even function, then it will be double, because if it's symmetry, what we have on the right side, on the left side should be equal. So we just calculate on one side and we double that. So give us 2 -12x 3x squared over 3, which is x cubed. 3x cubed over 3, so x cubed, go from 0 to 2. And we just put 2 in there. So if we do it by hand, little things that certainly help. So -12 times 2 plus 2 cubed. So -12 times 2 is -24. -24 plus 8, -16 times 2 is -32. Right. Because this one has a special limits of opposite number. Odd function will disappear. Even function will be double of each half. So we go to half of the boundary and then double. Yeah, so those little things will help you do the calculation. Right. So pretty much that's what the focus of the Green theorem. Instead of doing the line integral on the boundary, we do the double integral for the interior. The price to pay is that. Have to do that instead of the vector field. Right. Now we just write the green theorem in flux form. So instead of course, all the criteria is still the same. It have to be a closed, piecewise oriented counterclockwise, and the boundary is simply connected region. And we just evaluate. Right. In that case, n is the normal unit normal vector, but we're not going to even write that. We use this form or that form. Yeah. So use the Green theorem to compute our flux of the radial field. So that is the field across the unit circle. That is the unit circle. So this is. So I will write f dy minus g dx because that is the flux integral, or the integral in flux form, and this is the unit circle. Or counterclockwise, and according to Green theorem in flux form, instead of doing line integral, we can do the interior. The price to pay this time, derivative with respect to x, f of x, plus derivative of g with respect to y, dA. So in our example, the vector field is xy. So f is x and g is y. So derivative of f with respect to x plus derivative of g with respect to y. Derivative of f with respect to x is 1. Derivative of g with respect to y is 1. 1 plus 1 is 2. So bottom line is we just need to do the double integral on the unit disk, and that inside is just 2. And that pretty much equal to 2 times, and plenty of space here, so I just say flux integral over the unit disk and that is 2 dA, so give us 2 times the area of the disk, which is the area of the disk is pi r squared, the radius is 1, so just 2 pi. Right, so it turned out to be very nice. So there's a reason we write the line integral. In this case, usually we write f dx and g dy instead of writing that form, because write like this we know there's 2 components of the vector field, and also from when we write like that we know which one is f, which one is g, so we can calculate that part easier. Right, but bottom line is the Green theorem is very nice. Line integral on the boundary or double integral on the boundary in the interior, but we have to do that to go from the line integral to a double integral, so that's a small price to pay for doing that.